So hello again, everybody. Yesterday I was here presenting some work I did on performance modeling for GPUs. Today I'm covering a completely different topic, and that is sort of the first efforts that are going on in developing a machine learning ready sort of framework for numerical geodynamic modeling. Now, before I talk about anything, I just want to give you, again, a brief table of contents just to help you in following this presentation. I want to start with a little bit of an introduction and motivation. Of course, following up Taras's talk, it is maybe already sort of, he already gave you an idea of why machine learning would be a very interesting sort of field of technology to apply in these problems. But still, I'll give you a few examples on where we can use machine learning. I'll give you a very, very brief scientific background on some very basic geodynamic modeling examples. Of course, it's not going to be anything as complicated as what Taras discussed, so we're taking baby steps, you know. I'll talk a bit about which type of discretization and simulation techniques we're using for these type of problems. And then I will present a multi-grid method that I've been working on to sort of power a Python-based solver that is fast, scalable, and GPU-enabled, and of course is compatible with whichever machine learning library you want to integrate into this workflow. And finally, I will give show a little benchmark about a 2D buoyancy-driven flow example of material sort of advection. Okay. So what was the initial motivation for all of this stuff? Well, I was working on some machine learning super resolution tasks, and the idea was that, okay, it's really expensive to run a fine grid simulation, so what we can try and do is run a coarse grid simulation and then upscale it using some super resolution model. This is done very often in computer vision. There are a number of different models that work quite well. And so the idea was, if it works with images, let's try and use the same type of technique, but for scientific data instead. Of course, you know, adding some physics information into the training loop, but essentially that was the idea. And then we sort of hit the problem. Of course, geologists are not computer or computational scientists. And so they often work with sort of these ad hoc solvers that have been written in a bit of a heroic way, as Taras said earlier, in C or MATLAB or Fortran or a number of different languages. And the problem is that it is very, very difficult to introduce machine learning methods in this type of pipeline, especially for someone who doesn't come from an HPC background and is not, maybe doesn't have a very strong programming background or doesn't know all of the available libraries and all of these details. So what are the goals, or what are the problems that I wanted to fix when I started working on this? Well, the idea was to build an efficient, extensible, and simple to use framework that supported all of the different SciML workloads. So for example, you can integrate multi-layer perceptrons or convolutional neural networks, physics-informed neural networks, or even solver-in-the-loop type of differentiable physics applications. And while I was at it, well, let's just try and fix all of the other problems that sort of plague current state-of-the-art solvers. So things like poorly written or inefficient code, where you have a simulation that might run for months before yielding sort of the final results. No parallelization or little parallelization, no GPU support, no NPI support, all of these things. And also having sort of very confusing and impossible to debug code that people coming, you know, from outside to the group or geologists really struggle dealing with. Now, I mentioned that I would discuss some applications of machine learning in geodynamic modeling. Of course, Professor Mishra yesterday gave a very nice talk about different sort of applications that machine learning can have in scientific simulation and numerical modeling. But of course, I'll just go over a few for this specific context. One option or one sort of a prospect is to model unknown or poorly understood processes, for example, with neural operators, which is the type of models that Mishra talked about yesterday. You can try and resolve physical processes that happen at a subgrid resolution. Now, of course, if it's something maybe a little bit simpler, like heat dissipation at a subgrid level, you can do that analytically. But definitely, you can try and model more complex physical phenomena at a subgrid level using, for example, solver-in-the-loop type of optimization methods. You can apply physics-based correction. So, for example, refining solutions with a physics-informed neural network, or enforcing conditions that are otherwise very difficult to do analytically. And of course, you can also do things like detect localized events in long simulations. Oftentimes, we work with rectangular or even regular grids. So this is like a prime application of convolutional neural networks for classification, for example, where maybe you run a simulation for millions of years and you have some very localized, very sort of, especially in time, event that you're interested in, and so you can avoid having to manually scrape through all of this data and just detect only the interesting parts of the simulation. And this is where I get to the software I've been building. I decided to name it Pyroclast, and the reason is it's a bit of a play on word. Pyroclastic rocks are sort of the rocks that are shot out during explosive volcanic eruptions, and I found it kind of funny that it already started with the prefix pi, which is usually used to indicate, you know, some type of Python library or a project that is implemented in Python. But again, the point is to have a simple, extensible, and modular framework that offers a lot of reusable code and routines. It has to be fast, and to do this, I try to combine different technologies to achieve high performance. And of course, the idea is really to push parallelism. So shared memory, MPI, and GPU type of parallelism. Of course, you know, this is still a work in progress, so a lot of this stuff I'm still working on, but this is sort of the vision for the project. And yeah, of course, I already mentioned this, but I wanted to write this in Python because it's when developing these complex models, it's really crucial to be able to iterate quickly and test different things and try out what works and what doesn't. So Python makes it very quick to iterate on ideas and test out different things compared to having to recompile your whole workload every time, especially if you're not someone who's very comfortable with that type of work. And of course, yeah, the idea of natively supporting machine learning frameworks like PyTorch. So let's get into geodynamic modeling. We already had a very nice presentation for the past hour, but again, some of the points that I wanted to make just to give a quick intro. What is geodynamic modeling? Well, essentially, we're simulating the Earth's internal processes to understand physical phenomena like plate tectonics, mantle convection, and subduction zones. And the purpose is really to explore how heat, gravity, and material properties drive these geological phenomena. And there are many applications for this type of research. You can do things like try to predict volcanic activity, earthquake mechanisms, and mountain formation, and really many other applications of the sort. And the reason why this matters is because it provides sort of insight into the Earth's past, present, and future evolution. Now, I want to discuss a bit the key computational methods that we're using when working with this type of simulation. In terms of physics, at least for these purely geodynamic models, we often work with continuum mechanics and conservation PDEs, so things like the continuity equation, the Stokes equations, the heat equation. And in terms of numerical methods, at least what I'm focusing on is the Markov-Insel method, which is essentially a hybrid Eulerian-Lagrangian method that uses both a Eulerian staggered grid to solve the PDEs with a finite difference scheme, as well as Lagrangian particles that are used to compute very accurate advection so that we avoid sort of numerical diffusion. And the result is essentially this kind of multi-physics finite difference solver with particle-based material advection. Again, the idea of this Markov-Insel method is to mitigate numerical error introduced by moving material properties. This is especially important in this context because we have very sharp and very extreme properties. So really going about it in a different way, for example, trying to compute advection directly on the Eulerian grid introduces too much error that accumulates very quickly. And so, again, these material properties that are subject to advection are prescribed on these Lagrangian markers. So things like density, viscosity, temperature are moved around on these particles. And once you've moved these particles, you interpolate the properties back to your grid, and you solve your PDEs on this Eulerian grid. Now, in terms of 2D buoyancy-driven flow, we're only concerned with the mechanical part of the simulation, so no thermal component, no energy conservation or things like that. But we're essentially solving the continuity equation. At least in 2D, this is divergence equals 0. And the Stokes equations for slow flow, which are discretized in terms of the deviatoric stress tensors and then reformulated in a pressure velocity formulation. And on the right, you can see the type of grid that we obtain. So you can see that not all quantities are defined at the same locations, and this is to ensure numerical stability during the solution process. So I want to give you a bit of an overview or diagram of what a solver or like this kind of solver looks like. So we start by interpolating the marker properties from these particles to the staggered Eulerian grid. Then we solve the momentum and continuity equations on the grid. We define a marker advection time step, which is required to enforce stability of the simulation via the Courant condition. We interpolate the velocities that were computed on the grid back to the markers, and we use these velocities to advect the markers using a Runge-Kutta scheme usually. And from there, we return to step 1 and begin the next time step. So really the challenge of this is essentially implementing these 3 steps, these 2 interpolation steps plus the solution of the linear system in Python in a way that is fast, parallel, efficient, easy to use, and has all the bells and whistles that we want and that I discussed earlier. Okay, so we've established what the problem is. Now I want to give a bit of an insight on how I decided to structure this solver. I've organize it in a very object-oriented programming approach. So you have 3 main objects that drive the whole simulation. You have a grid that is responsible for, of course, the grid, a marker pool, which is responsible for moving around the markers and all the advection process, and then a model object that is responsible for the multiphysics iterations. Or in this case, there is no multiphysics, but that's the point. And the reason I did this is because you can mix and match different grids and marker pools and models in order to reuse as much of the code as possible. We really don't want users to have to rewrite all of the code every time they try and use a new model. And of course, I try to follow a few rules for writing fast Python code. Of course, try to work with arrays as much as possible in Python. I heavily rely on a JIT compiler to optimize code and write CUDA kernels, and this is Numba. And of course, I prefer try to run tensor operations on GPUs via CuPy whenever possible because the tensor cores are really fast. For those of you who aren't familiar with Numba, it's a very, very great tool that allows you to take code written in Python, but with sort of C-style paradigms, explicit for loops and stuff that usually you don't really want to do in Python because it's very slow, and it will translate this code into an intermediate language and then compile it via LLVM, and this allows you to tap into OpenMP directly from Python and apply a number of different optimizations like vectorization and all of this kind of thing. So you can write fairly low-level code directly from Python, which is very, very, very nice and very, very useful. So how do we discretize this system? Well, this is where things go south. Discretization leads to a saddle point linear system. And the intuitive reason for this is that the momentum equations determine velocity, and that's fine, but then the continuity equation determines pressure. So we're supposed to solve for pressure from the continuity equation. But the problem is that the continuity equation has no pressure term inside of it. So it becomes kind of difficult. It only sort of determines pressure indirectly. And this results in extremely numerically ill-conditioned problems that are very, very difficult to solve. For small 2D problems, we can get away with doing some matrix scaling or other type of preconditioning and then doing a sparsal view factorization. But the problem is that even when you get into large 2D problems or even small 3D problems, then LU factorization becomes way too expensive, and we need to develop an iterative solver to solve this type of problem efficiently. And the solver of choice here is a geometric multigrid solver. Luckily, we're working with very simple domains, usually rectangular. So geometric multigrid is the perfect choice in this case. So the idea of a multigrid solver is that you solve the same problem on different grid levels, which have different resolutions. The high frequency errors are smoothed on, or like are solved for on the very fine grid, and the lower frequency errors are reduced on coarser level grids via sort of residual correction. And the idea is that on the coarse grid, information sort of propagates much quicker compared to working directly on the fine grid. And again, the idea is that you do a little bit of smoothing on the fine grid, then compute the residual, interpolate that to a lower sort of coarser grid, fix your sort of residual correction on the coarser grid, and then interpolate the solution back to your smooth grid and try to fix and clean up again your original solution. And you do this in a cyclic way multiple times in order to solve your problem on all grids at the same time. And the problem here is, again, how do we design a smoother that allows us to solve these intermediate problems? This is also non-trivial, because standard smoothers like Jacobi iteration or Gauss-Seidel just do not work for saddle point system. And there is a very nice trick that you can do. You start with your saddle point linear system, which has this very ugly zero corner in the lower right-hand side. And what you do is you try to solve this in a block Gaussian elimination type of way. And what you do is you first solve for velocity by only considering the top row. And what you get is this expression for the velocity vector u. From there, you plug this definition into the second equation, and you form this Schur complement type system, and where the BA inverse B transpose pressure is the Schur complement of the matrix. And of course, we cannot actually form this Schur complement because it's very expensive. So what we do is we apply Richardson iteration to that linear system and obtain this update formula for pressure. And from there, we use our original definition of velocity, except we say that the new velocity is, or velocity at cycle k plus 1, is defined in terms of the pressure at cycle k. And this gives us a very nice smoother that we can use for this type of problem. So we first solve for velocity, and then we update pressure based on the obtained velocity. And this is known as a Uzawa type iteration. Now, if we try and put it all together, what we get is a fully coupled geometric multigrid solver that is implemented in a completely matrix-free way. So none of these matrices are actually ever assembled. And the neat thing about this is that it uses a full Uzawa iteration at each level. Normally, what you see is that you only apply a multigrid method to solve this the first system, or the first step of the smoother iteration for velocity. But instead, what I've been doing is solving for both for pressure and velocity using a multigrid scheme. The direct solution of this intermediate linear system, AU equals F minus B transpose P, is very computationally expensive, of course. So what we do instead is approximate the velocity via a few iterations of Gauss-Seidel. Specifically, we want this to run very fast, so we're using a variation called red-black Gauss-Seidel, which runs very well on GPUs. It essentially is it uses some smart indexing to make classic Gauss-Seidel parallel and achieve similar performance to Jacobi iteration, but without having to incur the penalty of using a Jacobi method. Furthermore, there's like a preconditioning step applied to pressure before the update that is based on the local viscosity field. And there are other options that I've been playing around with and I've implemented. You can use Krylov methods as a sort of accelerator instead of a Uzawa smoother on the finest level. And this can be either BCG stab or GMRS. Of course, we can also use this whole geometric multigrid solver as a preconditioner itself for a Krylov method. And I've implemented also a type of sort of distributive pressure relaxation, which is essentially the idea is whenever you uptake pressure via your Uzawa iteration, you correct velocities on the fly in order to try and sort of modify the residual of the velocity equation as little as possible. So let's get into the GPU support. Of course, there's a bunch of different technologies that are, or methods that are sort of stacked in together into this solver. And the question is now, how do we make this efficient on GPUs? Efficient parallelization of this is not trivial. And the reason is that you're solving a problem at very different resolutions. And so the complexity and parallelism of each level, or of each sub-problem, is very different. Specifically, on fine grids, you tend to do few iterations of this smoother, with each one having high amounts of parallelism. So they're very parallel and high-resolution grids. On the coarse grids, on the other hand, you have many iterations of sort of a low parallelism problem, because the grid is small and you cannot parallelize operations on the grid, and of course you cannot parallelize iterations themselves. So what you end up doing is this hybrid GPU-CPU strategy where you define a threshold and essentially decide whether to offload computation to GPUs only when the problem is large enough. So above this threshold in your sort of multi-grid cycle, what you do is you just push the grid on the GPU and solve using stencil operations on the GPU. And under a certain threshold, you instead just run it on the CPU, maybe with OpenMP or sort of shared memory parallelism. Once you get to the very coarse grid, what ends up happening is that you have a large amount of iterations on a very, very small grid. So instead, once you get to that level, it's just often better to ditch the iterative process, assemble a local matrix on the fly, do LU factorization, and just solve it with a direct solver. So we have essentially three components. We have a direct solver for the very, very small problems. We have an iterative CPU solver for the medium problems, and a GPU solver for the large problems. Now, one of the key points that I wanted to discuss is how do we scale this up, because this is a challenge, of course. I have some ongoing work on scaling up this solver across nodes using MPI for PY. And what is very nice about this is that we can simply use domain decomposition on the fine grids because I'm not actually ever assembling any matrices. So everything is completely matrix-free, so we do not have to deal with sort of a distributed sparse matrix object, which is often very, very annoying to deal with. Another benefit is that communication is minimal, actually. All of these smoothers, especially if you're not using any Krylov accelerator at the finest grid, really only need some neighboring information. And so you can get away with just doing ghost cell exchange between iterations. So there's really very little communication if your domain is large enough, because you only have to move around sort of the very thin slices of data, right? The boundary data between each subdomain. Now, of course, we still have the issue of medium and small grids. You cannot distribute those, of course, because they're way too small. So essentially, there are two options. Either you store and solve these problems redundantly on every rank, or you do some sort of gather to rank 0 and then have a centralized solver and distribute the results back, which is not ideal, but unfortunately, there is no way to solve this type of problem in a purely distributed setting. So finally, I want to conclude with a little benchmark. This is a 2D floating square block of material with a density contrast, essentially. The idea is that we have a rectangular domain. We plug in this very sharp sort of square block of lower viscosity and lower density material, and it starts to float in our domain. And this is, for example, the type of velocity field you get, you can see that it has these very sharp corners and sort of high intensity regions next to the corners of the square in the middle. You can sort of make up the shape of the square. So it is a very difficult problem to solve, especially with this type of viscosity and density with an iterative solver. And what I did is I tested the solver on a range of grid sizes, so going from small to large. Small is like 500 by 500, and large is 2,000 by 2,000. So essentially, if you were to assemble the system, this would be ranging from 750,000 by 750,000 linear system to 12 million by 12 million type of linear system. So very, very large, sparse linear systems. And the results show that in all the cases, convergence is very, very fast. You can see that in less than 40 iterations in the worst case, and probably you can see it's a bit jagged, so I could have done some parameter tuning to get it to converge better, but we get to machine precision, essentially levels of accuracy, which is absolutely comparable to what you get with a expensive direct solver. And the nice thing is that even in the largest case of the 12 million by 12 million system, the actual compute time to solve this system is 40 seconds. So it's very, very fast, especially compared to the hours that it would take using a direct solver, even in a parallel setting. Now, of course, this is even a bit of an unfair sort of comparison because I am starting with a very, very bad initial guess. So this would be a simulation of the first iteration of the solution process where I don't have an initial guess for any of the sort of pressure and velocity fields. While if I were to start or to compute further iterations, in time, what I could use is the previous guess or the solution of the previous time step as an initial guess, and that would drastically improve both convergence rate and time to solution. All right, so this was my my presentation. Thank you for your attention, and if there are any questions, I would be happy to try and answer to the best of my knowledge.
Thank you, Marcel. Any questions?
Much, Marcel. For these type of problems, it's highly relevant if the method also works when you have very small scale heterogeneity in the viscosity field, which are not resolved by coarser multigrid levels. Did you try to use it for the methods where instead of, say, one big high viscosity block, you have instead lots of these small things that are interacting, and then how well will it work in this case?
Yes, it's true. That is one of the limitations of these sort of geometric multigrid methods, and it is one of the reasons why I was experimented with using a Krylov type smoother as the sort of highest level or finest grid. Essentially, what I observed is that not only Krylov methods tend to perform a little bit better in terms of getting more accurate solution, but they're also more stable. So one other example where you can still obtain a good solution, where with purely geometric multigrid you would need sort of more advanced consideration, is when you have very high viscosity contrasts. I'm sure you're familiar with this type of problem. If you just try and apply normal geometric multigrid, you don't get the correct solution. But if instead you run your Krylov solver as an accelerator at the top, or you use this geometric multigrid method as a preconditioner for example, GMRS or BCG stab, then you still get a correct solution even without having to do any trickery with like rescaling viscosity contrasts and things like that. So that's sort of the status at the moment.
Hi, can you hear me? Yeah. So you mentioned that you put a threshold to decide whether to run part of the simulation on CPU or on GPU, and I was wondering whether you have, I mean, you could benchmark that and decide that. Do you have something more dynamic, say?
At the moment, no. So all of this is very early in development. So essentially what I do is, at this point, just plug in different numbers, see what works, see what doesn't. And maybe I should mention this actually. This data I generated before I had a GPU implementation. So this is pure CPU running on 16 CPU cores. So I don't even, on some old, I think it was AMD EPYC 7742 CPUs from like 5 years ago. So yeah. If you get this to run on GPUs, it's going to be much more faster, but at the time, GPU support is sort of experimental. I'm getting there, but I don't have things like dynamic sort of threshold yet implemented yet. Likely, since most of the times you work with by sort of dividing the resolution of your grid by 2 or by a constant factor, you can likely figure out a way so that based on the sort of scaling factor that you use between grids, you always end up having a threshold that fits the type of GPU, but at the end of the day, you still have to benchmark which resolutions run best on GPUs and which on CPUs. There's no really going around that, in a sense. But what you can do, again, is have it so that if you change the resolution of your grid and the scaling factor, you always sort of offload the correct sort of resolution dynamically, in a sense, or the correct level dynamically.
I have a question for you, and you mentioned the 3 size problems, and one that fits on the kernel, one fits in the CPU, and one fits in the GPU. So what's the threshold between these, and from a dimension point of view, to switch between and decide where it goes?
That's a difficult question to answer. And the reason is that it is hugely implementation dependent. So what I've noticed is that on CPUs, really past, let's say, smaller than 500 by 500, it really starts to even scale poorly on CPUs, and on GPUs you likely need at least like 1500 by 1500 to get some substantial performance improvement. The problem is that all of these sort of resolutions are based on the current implementation that I have, and if I were to optimize more, all of the routines that I'm using to compute these results, then I would have probably better efficiency in terms of parallelism both on CPU and on GPU, so I could shift down sort of these thresholds. So it's very difficult to give you an exact sort of threshold, and ultimately you just have to benchmark your system, see, run a few tests and see what works and what doesn't. So that's sort of the bottom line.
Any last question? Okay, thank you, Marcel. Our next presentation comes from Giordano Manzini.